So let's consider our visualization when we think about the possibilities for tuning MapReduce. So again, we see that we have 6 different places where we have the opportunity to tune. Now we're going to start in this section and talk about physical tuning. There's a lot of tuning that we can do through our MapReduce code, but it has to work in conjunction with physical tuning. And this relates to physically what the data looks like when it comes in, where it lives, what's the capacity of the system that it's being processed on, what's the connectivity to the output location, and the capacity of the output destination as well. So you can think of it as a cycle. So you can do optimization on the upper right before the job runs. So what are some kinds of optimizations that I've completed before jobs run? Well, I mentioned it earlier, but I'll call it out again. The most common one is pre-processing on the data. So what does that look like? I might take text data and do something like remove all the non-English characters, remove all the punctuation, or do some other type of parsing just to make the actual MapReduce, if for example, I'm analyzing the words for maybe sentiment analysis, a little bit faster and easier. So pre-processing on data is a common optimization task. Now you can also optimize on load of the data. How you might do that is you might change the compression ratio, for example, so that the size of the data is actually smaller. You might break the data into different sized chunks. You might change the scalability of the data load. This is particularly an option if you're using cloud-based Hadoop scenarios where you can spin up additional data nodes and spin them down quickly and cheaply. Then you're going to optimize the map phase of the job, and that usually deals with code and how you write the code. So we'll look at that in greater detail in another movie. You can also optimize the default shuffle phase of the job. That's a highly complex task, and it's something that in production I've only seen a couple of times. So my recommendation is to let that execute in the way that it's designed unless you have a very compelling business reason to make a change to it. You can then optimize the reduced phase of the job. I see this happening less frequently than the map phase. I'll be giving you some techniques in subsequent movies on how to do that. And you can also optimize after the job completes. Now what could happen there is you could take a really bulky job and you could break it into 2 jobs so that the first job was more lightweight and processed more quickly, and possibly using greater parallelization so that the second job could process in a more timely manner. You really want to think in terms of chunks or Lego bricks when you're thinking in terms of MapReduce design. So I talked about optimization before running a MapReduce job, and I talked about a lot of the items on this page, but I'll just make sure to be inclusive. So I talked about compression, using a compression algorithm that's most optimal for your situation. And compression is a balance between how much compression you can get and how that compression affects the processing. If in your mapper you have simple logic, you can take advantage of a high level of compression. However, the opposite is also true. If you have very complex mapping logic, then sometimes you need to go with a more lightweight compression. Now, I didn't mention encryption. For some data, encryption is part of the business rules. You have to consider the overhead of working with encrypted data, which sometimes will entail de-encrypting it and sometimes won't. When we think about physical MapReduce optimization possibilities, the number one thing that I see out there in the wild is that the cluster configuration parameters have somehow been changed, and there's not a good business reason for those changes. People are just trying things out, and it's not documented. And what happens is on different MapReduce jobs, because we have non-standard configuration parameters, there's unexpected behavior. So if you're going to change from default cluster configuration parameters, make sure you have, number one, a compelling business reason. And an example of this would be if you want to change from the default replication of 3 nodes for each piece of data in HDFS to some other value, 2 nodes, no nodes, 5 nodes, for example. Have a compelling business reason for doing so, and make sure you document that so anybody else working with the cluster can understand. Another thing is you should take a look at both unused resources, so data nodes that aren't used during the majority of your MapReduce jobs, or overstressed resources, data nodes where you have a lot of spillage because your map processes can't fit into memory on all the data nodes. They spill out to disk, which takes a lot longer. From the highest level, are you using any sort of cluster monitoring tools? Now, we've seen in the Hue interface that we have lightweight monitoring, But this is part of the value proposition around the vendor distributions. They provide really industrial strength cluster monitoring tools that help you get the best value and the best performance out of a Hadoop cluster, and they're really worth investing in. One of the ones that I've looked at is Ganglia. There are many out there, probably tens if not 50 of them. There's a lot of different companies working in this space because it is complex, and you do want to make the appropriate use of the physical resources in your cluster. It's very easy, obviously, in a Hadoop cluster to just add more nodes, but you want to do it in an intelligent fashion and make sure that those nodes are actually being used because of the configuration settings and the MapReduce jobs that you're running through your Hadoop cluster. And I mentioned it, but the simplest possible optimization is to add more nodes. So again, you don't want to overlook the obvious. Hadoop is designed to scale, so especially if you're using cloud-based implementations, I find a really effective optimization technique when you're running against time deadlines, and maybe you have changes in your staff, so you can't rework your MapReduce jobs, some other complexity, just spin up more nodes. Another variant of this is if you have an on-premise cluster and it's getting stressed, and you really don't want to go out and purchase some more hardware, you can augment on-premise clusters with a partial implementation on the cloud. This is a sophisticated use of Hadoop, but I see really smart companies doing this where they'll offload some of their one-off batch processes. I've done this with some companies that process genomic information. They have the initial processing of the large amount of genomic information, which they need to aggregate and compare. They'll push that off onto an Amazon Hadoop cluster and use spot pricing, as I talked about earlier. They can get a really cheap and effective, quick process of a lot of data, and then they can pull that data back down and they can work on it locally. So this idea of mixed, both local and cloud-based Hadoop is really coming into play, and it's something for you to think about when you're optimizing from a physical standpoint your Hadoop implementation. As we think about tuning a mapper, let's trace through the path of data through MapReduce. So let's take a look here and start with the map. And the map will work with a key and a value. So let's call this key 1 and value 1. And that's going to be your info coming in. And how that comes in is going to be dependent on the data type and the default input split. That will produce, once the map logic runs on each node, a list of key 2 and value 2 pairs. Those are called intermediate values. There's going to be one list for each local node. By default, if we did something like a word count, it would be the word and then the number 1. So the 1, man 1, is 1, at 1, home 1, like that. So it's quite common in these types of situations to use an optimization that's called a combiner. What that is, it's a local reducer. What it does is it aggregates for each node, in this example, every instance of the same word. So if we had the word the 20 times, instead of listing it 20 times, we would have the 20. It would be a local combiner. Now this is an optimization that is really commonly used because then less data is passed across the network. It's so common, it's almost standard. It's not required, but it's a really, really common optimization. Now continuing on, once the output is run from the mappers, then by default, the shuffle and sort will run. And then the second part, of course, is the reduce. So looking very granularly on the right side, we've got the keys, and then we have a list of the values. And the reduce put into a list, which will make a new list of K3 and V3. There will be some intermediate aggregation done, depending on the amount of processing that needs to occur and the amount of resources on the reducers. And again, there's opportunity for you to look into that process and to provide further optimizations. One of the things at a high level is always keep your jobs as simple as possible. And if you feel like they're getting too complex, break them into 2 separate jobs. Back in an earlier movie, when I introduced the idea of MapReduce, I talked about the difficulty for OOP programmers getting their head around the MapReduce programming paradigm, which is really functional programming. One activity should be occurring, not 5, not 10, not really even 2 or 3. One type of process. So take the example of word count. In the mapper, we receive the text input, we parse it line by line, and we split that text into individual words based on some methodology. The default tokenizer uses spaces. You can write your own, as we talked about, but you have some sort of logic. Now, if you had to use complex A, B, and C, split, and then add, and then divide, and then manipulate, those should be separate MapReduce jobs and chain them together. It's a different way of thinking, but it's really the way the MapReduce API was designed to be used. So when we think of mapper task optimization, we have many different things that we can look at. The first thing I already talked about, which is subdividing tasks. That's the most common thing I see out there in the wild, where you need to break your mapper apart into separate mapper tasks. And as I said, you want to aim for really no more than 1, 2, or 3 processes to occur, and really it should be short. That should correlate to minutes, 1 to 3 minutes per map task run. Now, there's many other things that you can do in addition to this to optimize your mapper. You can, for example, set up a custom partitioner. The default is a hash partitioner. You can override that. You can partition by any value that's being passed in. That could be a numeric value, it could be a text value, a binary value, anything at all. Another optimization method is to reduce the amount of data. You can include logic in your mapper to skip those records that are determined to be invalid or bad. In your mapper, you can define what constitutes a bad record, and then you can also include a counter, and you can set a value at which the map job will stop or retry if too many bad records are found. You can also use this to assist in debugging or unit testing. Another optimization is you can monitor and tune for optimal spill ratio. So spill ratio means when the memory on the mapper machine is overloaded and the processing has to spill out to disk. That's what the definition of spill is. So the spill ratio is how many records spill out to disk versus those processed in memory. So the goal is the number of spilled records will equal the number of map output records. And you can tune this in io.sort.spill.%. And you can also set the desired number of mappers in the config files. I've already mentioned local reducers, which are combiners. Another optimization that you can do is you can set map-only jobs. No reducer. What's an example of this? Because this is a little bit strange when you first hear about it. One that I've seen is photo processing, where you pull in images and you pull them in as binary and you do some processing on them, and then when you're done with each map process, you simply pass them through because there's no aggregation that's needed. You're doing some sort of processing on each photo in this case. So let's look a little bit more deeply at input file compression. And I'm just taking what Cloudera uses. Vendors are different, so you're going to want to look at the vendor documentation. You really want to read what they recommend because their distributions do vary in how they support the different compression algorithms. So for example, in Cloudera, their version of LZO is splittable. So that compression algorithm you can write a custom input split for if you want to further segment the files. You always want to use the most efficient compression for your particular vendor or distribution. And I have a little chart here on the bottom that shows from Cloudera how much you can zip, what the size is, and what the decompression size is. As we're talking about compression, I want to remind you, thinking about data types in terms of mapper optimizations. You know from the code sample that we saw earlier that we need to work with writable types. So when we work with writable types in our mappers, we need to think about how the information is being compared and also sorted. Custom types are supported. So if you're not getting the performance or you're not getting the business logic out of the types that are available, you can create your own type. Now, there's quite a lot of code that you'll be writing for that, and you need to write a comparator. So an example of this would be geospatial data types. You need to test the performance of your comparator because, again, this is your logic, and you haven't had as much experience writing MapReduce code as the people from the open source community. So just, again, based on my experience, if you're writing your own type, you want to test with production levels of data the comparator function that you write. It's called a custom comparator, and often you'll also want to write a custom input split. So if you think about it, if you have geospatial data, how is that going to be split? It'll be split by default as if it's numeric data, and that might not make good business sense, particularly if you've got clumps of data in different geographic regions. Let's say you're a U.S. company and you do most of your business in New York and California. So if you split your data by the default method and you had a geospatial type, that really wouldn't work well when you were loading for MapReduce because you would not make maximum use of splitting the data across all your map nodes. You can also write a custom partitioner. Another tip I'm going to give you around data types is you only want to use the text type when you're using text data because there is a slight performance difference between text and the numeric types. And this comes out of recommendation from Cloudera. They see out in the wild that OOP developers tend to default to the text type even when they really should be using a numeric type. See it out there. So I'm going to talk about what I see in my production situations. So reducer task optimization usually falls into 4 categories. The first thing is, just like we did with the mappers, subdividing. So if you see reducers being overloaded, possibly you're trying to have the reducers do too much work, and you should break this into a separate job and just run it straight through another set of mappers and then through another set of reducers, so job chaining. Another reducer task optimization technique is logging or debugging, so that you can understand where the load is occurring. Because of course with the reducers, they don't run on every node of your cluster, unlike the mappers. They only run on some nodes. So you may need to dig into those logs to find out exactly which nodes your job is executing on, in which situations, which nodes it's not executing on, where the bottlenecks are occurring, if there are clumps of data. You can add a secondary sort into a reducer job, but when I see that, I really usually recommend to break the job apart. I prefer to have small separate jobs chained rather than beefy jobs that are doing more than one task. You can also set thresholds in the configuration like you can in the mapper, so that you can either kill long-running jobs, suspend jobs, get more information about jobs depending on the workload. So I have some more reducer optimization techniques. The first one is, from an architectural point, looking at the amount of work in your MapReduce job and saying, could part of this be broken into a separate job that doesn't even use a reducer? I made the earlier example of photo processing, and I actually do see that quite frequently because more and more different types of data is coming in. It's not just text data. So sometimes this data needs sort of a pre-processing that's highly distributed. So photos is a common use case. I've seen sound files or music files that need to be pre-processed, and they're just running map-only jobs. And then they're pulled into a secondary chain job to do the map and then the reduce. Also, you can use local reducers, as I've been talking about. It's a common pattern called combiners that run on the map nodes, and they substantially reduce the volume of data in transit to the reducers. We have one last optimization to talk about, and that's creating a distributed cache. So what this is, it's used to cache files, things like text files, archives, jar files, that are needed to run applications or jobs. How you use this is you include the path to the file via a URL in the job configuration or job comp settings, and the paths can be to a location on the HDFS file system or on HTTP. The files will be copied to each data node on each job execution for the mappers, and are often used in scenarios like lookups. This is found in this library, org.apache.hadoop.mapreduce.filecache.distributedcache. Now let me take this example a little bit further. Let's say you are using a lookup as part of a map job. Maybe something like a business identification code, and then you wanted the name of the business to be output in the key value pairs. And you had a master data file that identified all your businesses or all your customers by number. So that would be a common scenario for this. Now, we've reached the end of our tour of MapReduce job optimization for MapReduce 1. Add more nodes. Again, you want to go with the low-hanging fruit first. You use MapReduce and Hadoop because it's highly distributed and highly scalable. And if you think about it, although you can tune almost any knob or widget in the MapReduce algorithm chain, it sometimes takes a substantial, large amount of time to understand how to tune it properly. And it's just cheaper and faster to go buy more nodes. Now that being said, that isn't always the answer. I generally start with more nodes, and then I will continue to profile to see where the bottlenecks are occurring. Sometimes it can be kind of a band-aid solution. Just like I said, go up on the cloud with some of the loads so you can get more nodes on the cloud, and then come back down and see what's causing issues in your cluster. And you'll notice we talked about all kinds of different optimization. We talked about physical optimization on your cluster configuration settings, and optimization before you run your MapReduce job, after you run your MapReduce job, and then within it. There are really many places to go. How do you know where's the right place? Instrumentation, logging, and management. So it really is important as part of any enterprise implementation of MapReduce that you have a plan and a set of tools that will allow you to easily manage and monitor Hadoop. This is something that I hear all the time from an architectural perspective. It works in the development environment. I go to production and it just blows up all the time. This is particularly the case with Hadoop because the scale we're working with here is very different than the scale of relational databases. Something where you have a really small amount of data is going to be running substantially differently on a local machine than it will on a 100-node cluster. So you want to invest not only in tools, but you want to invest in load testing. It's really, really important when you're moving into production situations that you spend the time before you move a solution into production testing with production level load. And again, my big tip here is to use the cloud because it can be a lot cheaper to spin up temporary clusters with large amounts of data on the cloud, figure out what you need to tune, then come back and fix it locally before you deploy.